Hi, welcome to video 4.5a, Introduction to Integration by Substitution. So, there is no product rule, there is no quotient rule for integration, so when they get ugly, we're going to have to deal with it. And the way it's going to work, so you know that the integral of x squared dx is x cubed over 3 plus c. Integral t squared is t cubed over 3. Integral u squared is u cubed over 3. So what's going to happen now is we're going to have an ugly thing. Because remember that property where we add 1 to the exponent, that's just if it's just a variable. And right now it's a little bit uglier than just a variable. So the strategy is to let u, for now, the first strategy, missing an a there, is let u equal the contents of the parentheses. Okay? So remember, pretty is just x. Ugly is anything else, 2x, x plus 5, x cubed, sine x, whatever. So here's an example. We have x plus 5 to the 13th. So what we do is we let u equal the contents of the parentheses, which is x plus 5. Now, this is important. You can't stop there. You then have to ask yourself, what is du if u is x plus 5? So if I took d dx of each side, I'd get du dx equals 1, right? And then I could send the dx to the other side. So what we'd like to do is just go directly to here. If I take the derivative of the left, I get u. I take the derivative of the right, I get dx. Okay? Now, the key thing here is just like here where this x had to match this x, this u has to match this u. So you have got to have the derivative of whatever this guy is here, this u, in order to do what we're about to do. So our u is x plus 5, so x plus 5 to the 13th is u to the 13th, and we just found out that du is the same thing as dx, so I can replace dx by du. I can now integrate u to the 13th du into u to the 14th over 14 plus c, and then at the end I replace the u back by x plus 5. You cannot stop here. The question had no u's in it. We're the ones that are introducing the u in order to be able to solve this. So what you need to do is make sure your answer is back in terms of x. And remember, u was x plus 5. Okay? So this is just reminding you the only time you can do this is if you have pretty something. And in this case, it's pretty u. Okay, so here's another one. If you have the integral of 3x minus 7 to the 4th, now you know the integral of x to the 4th dx is x to the 5th over 5 plus c, which means you know that the integral of u to the 4th du is u to the 5th over 5 plus c. So we're going to let u, like we've been doing, let u equal the contents of the parentheses. So your u is equal to 3x minus 7. You have got to right away figure out your du, and your du, I know I can do this. Your du would be 3 dx. Now, again, you can think of it as du dx. Take d dx of each side and then send the dx to the other side. Now, there's different ways of doing this, but this is how I like to do it. What I like to do is say, you know what? I need a du because I've called this u, so this is going to be u to the 4th. I need a du here. I need 3 dx. And so what I do is I introduce the constant 3, and then I counteract on the outside with 1/3, and it's times 1/3. So really I've introduced times 3 times 1/3, which means I've introduced times 1, so I haven't really changed anything. And therefore I can now replace 3 dx by du, and now I have 1/3 the integral of u to the 4th du, which is 1/3 u to the 5th over 5, which is plus c, which is u to the 5th over 15 plus c, and do not leave that as your final answer. Remember to go back, and we had called u 3x minus 7. So this is not very difficult. Now, you might look at this and go, oh no, there's this extra variable here. That's actually a very happy thing. Be very happy that it's there. So strategies. So far we've said let u equal the contents of the parentheses. It could be let u equal the contents of the radical, because you can think of a radical like a square root as something to the half, so it's parentheses. And if there's two polynomials, let it equal the polynomial of the higher degree. So what I'm going to do is I'm going to let u equal the contents of this parentheses, which is 3x squared plus 7. My derivative for that is du equals 6x dx. That's why we're very happy we have the x, because you cannot introduce and counteract a variable, because you're not allowed to bring a variable on the outside of an integral. You can only counteract with a constant, so which means you can only introduce a constant. If we hadn't had that x here, believe it or not, the only way to do this problem would be to actually raise this stupid thing to the 10th power. And that would take 40 minutes. Anyways, so I know I need 6x dx if I want to replace it by du. I've already got the dx. I've already got the x. I need to introduce the 6, counteract with a 1/6. I now have 1/6 the integral of u to the 10th du, which is 1/6 u to the 11th over 11 plus c, which is u to the 11th over 66 plus c. And then again, don't forget at the end, you have to come back and replace u by 3x squared plus 7. Now, shortcut, if you feel comfortable doing this, is kind of picture in your head that your u is 3 at the contents of the parentheses. Picture in your head that du is 6x dx and go, oh, look, I'll just introduce a 6, counteract with 1/6. Okay, in BC, they get to the point they don't even need to do the introduce the 6. They just automatically counter with 1/6. Okay, so here's another one. Again, very straightforward. Let u equal the contents of the parentheses. What's the derivative? du equals 3 dx. I've got the dx. I need to introduce the 3, counteract with a third. I'm integrating 1/3 integral u cubed plus du, which will become 1/3 u to the 4th over 4, which is actually u to the 4th over 12, but u is 3x plus 5. So now it's 3x plus 5 to the 4th, all over 12. Don't forget your plus c. Again here, why does this look like the other one? Oh, it's close though. Okay, again here you're going to let u equal the contents of the parentheses, which is your x squared plus 5. The derivative of that is 2x dx. Thank goodness I have the x and the dx. Introduce the 2, counteract with a half. I have 1/2 the integral of u to the cube du, which is 1/2 u to the 4th over 4. Which is u to the 4th over 8, but don't forget to replace u by x squared plus 5. Okay, here's another one. The first thing I would do is I would bring this 5 on the outside, and I would bring this 2x minus 5 cubed that's in the denominator and bring it up here and make it a numerator with an exponent of -3. I'm going to let u equal the contents of the parentheses, which is 2x minus 5. The du is 2 dx. I've already got the dx. I introduce the 2, counteract on the outside with a half. I now have 5/2 integral of u to the -3 du. Integrate that, you get 5/2 times u to the -2 over -2, which becomes -5 over 4u squared plus c, and of course you have to change the u back into x's, and the u is equal to 2x minus 5. Okay, I do want to look at these in the book because be careful. All they're asking you is what's the u and what's the du. Notice they're not asking you to actually integrate this, okay? And really what we're doing is kind of a reverse chain rule, but you don't need to worry about that, okay? So if you were looking at these, obviously here you'd let u equal the contents of the radical, which is x cubed plus 1. Your du would be the derivative of that, which is 3x squared dx. For number 14, what will happen with trig functions, and we'll see that in a bit, you'll either let u equal the whole trig function or sometimes just the angle. And here it'll actually be best for us to let u equal the angle 2x, therefore your du is 2 dx. Okay. This is an interesting one, cosine x over sine squared, which is sine x to the -2 times cos x dx. If you let u equal sine x, the derivative of sine x is cos x dx. So notice I'm letting u equal the entire trig function, right? Whereas here, I let u equal the angle of the trig function. But here I'm going to let it equal the entire trig function. So this becomes integral u to the -2 du, which etc. becomes -1 over sine x plus c, or negative cosecant x, same thing.